recording here. Okay, well, plug us in here. All right, so I was looking through the notes for kind of the second section of chapter 9. Looks like I must have run out of time or something last year, so looks like there's only one example, but that's okay. That should be enough for us to work through today. We've only had time to work through one anyways. Oh, and I realized I forgot to fill in those examples last day before I posted the notes, so I reposted the notes just this morning. So if you have the old ones, then maybe just replace those with the ones that I just posted this morning, because they have all the examples worked up. Okay, so let's see here. So today we are doing the last section, right? We're cutting 9.3, the chi-squared, because we decided, you know, with everything that's going on, it didn't really make sense to do it. So, and we would have run out of time anyways. So today is April 6th. I guess I can put 2020. And I think I've been putting box around it or something. We're doing chapter 9. Part 2. Okay, so what did I just make a note of here for you guys? Oh yeah, so on Wednesday, we will do final exam review. And so we're meeting, all the stats teachers are meeting later today. And so I'll have a good idea, or I'll know exactly what the final exam is going to look like on Wednesday. So I'll give you the outline then. Unfortunately, I don't have it now. I don't know what it's going to look like. So just kind of stay tuned for that. And, but I will post, so I will post a final exam review. It's just going to be a bunch of questions. Figure out what type of questions there are, right? So, oi, what the, don't know what happened here. Okay. So here, so what I mean is there's going to be a bunch of different questions. And so as a starting point, I want you to figure out what type of questions there are. I'm going to go through and make sure that there aren't any questions that we didn't do this term, right? So if there's chi-squareds, I'll have to pull those, but I don't think so. So it should be pretty well ready to go. But you have to figure out what type of question it is, and it'd be really good if you can do that before the review class. Do this before Wednesday. Oh. And in fact, oh shoot, I don't have it. I'll have to find it, but I'll post it right after the class when I post these notes too. So, all right, so it'll just be a bunch of questions, and just try to read the questions. So don't even necessarily do the questions, right? Just read the questions and try to figure out what type of question it is, because that'll point you in the right direction of the formula sheet, right? And so just figuring out what type of question you have is going to make things so much easier. So if you go to your formula sheet, right, we've got a bunch of different types of questions, and I am talking about, well, I guess there could be a regression question, right? And so for the question types, We could have regression questions. There can be probability questions. There can be, I don't think there's going to be anything like this on the final, but like I said, I'll know better after today. There can be Z-score questions. There can be binomial questions. There could be Poisson questions, although I don't think I have any Poisson on my review. There could be one sample, sigma known, sigma unknown, paired samples, or independent samples. So 2 independent samples for means. And then finally for proportions, you could have 1 sample proportions or 2 sample proportions. And this is the one that we're wrapping up with today. Notice that there's a lot of information here on the formula sheet, right? But we're just gonna dissect it, and it's really not gonna be as bad as it looks. So I'm gonna check back for questions here. I haven't seen any, but who knows? Morning sky. Nope. Okay. So let me know if you have any questions, but oh, when is the final? So the final exam is going to be in the regular slot. So the final exam is still on the 21st from 9 to 12, just no room. So I'll put that in the notes actually. It is on April 21st. And that should be just across the whole campus. We're supposed to keep the final exam dates the way they are. April 21st. I think we were 9 to noon. So, and then the next question was, are you deducting marks off of the lab Dropbox? No, I'm not sure what that means. No, the lab Dropbox doesn't do anything. That just opens up the quiz for you. And then, is it online? Yes, it is online. It might be a mix, so that's what we're deciding today. So it might be a mix of kind of written work that you send to me, or just a pure Moodle quiz if we're able to get something working that looks like it's going to capture everything. So, so Harmon, I don't know. Awesome. For the lab Dropbox, no, it doesn't do anything. It just opens up the quiz for you. Okay, but like I said, so the details for the final, okay, awesome. I'll have after our meeting today, so, but it's later today, so we'll see. Okay, so let's get started here. So our last kind of question type is 2 sample proportions. So we saw two sample problems with means, right? Where we want to compare the mean of group 1 to the mean of group 2. And so now we're doing the same thing, the proportion of group 1 to the proportion of group 2. And so we're now comparing proportions of 2 categories, right? So categories are what yields proportions. And so, and I found a silly typo here. Let me see here. Okay, so if we got a better mark on our test 2, will that now be worth 40%? It won't be worth 40%. I'm still gonna keep, so what I will do is, like I said before, I will use the distribution that benefits the class as a whole. Okay? And so what that means is just I'll look at everyone's test 1 grades, everyone's test 2 grades, and so I'm not going to look at how each individual did, but just as a whole, what the distribution is going to be, then I'll use that. Okay, so because that way it's fair on average. So, okay. So, oh yeah, where's the typo that I wanted to show you guys? Let's see here. Oh yeah, the assumptions we need to check, only check slightly, only change slightly. All right, so we had to check assumptions for 1 sample proportions, and remember it was different depending on if we were doing a hypothesis test or a confidence interval. That's going to stay the same, but just like for the means, right now we're going to have a sample size of group 1 and a sample size of group 2, right? And so, and we're going to have p hats, q hats, or we haven't really been using q hats, but you should know what they are, right? 1 minus p hat in that case. And so we have to check the assumptions. The assumptions are just extended because we have 2 sample proportions instead of just the 1, right? And so that's going to be the difference. So we still have to have independent observations, and so we have to have random samples. That goes for both of the samples, right? So we have to argue that both of the samples were randomly selected. And then the 10% condition, right? We need to have big samples, but not too big. So the group 1, the sample size for group 1 has to be less than 10% of the population of group 1. And then the sample size for group 2 has to be less than 10% of the population for group 2. The normality condition, right, depends on if we're doing a hypothesis test or a confidence interval. And so for the hypothesis test, we need at least 10 expected successes and failures, but we use the pooled proportion, which is on your formula sheet, but also I'll point this over here to the margin, where the pooled proportion is the number of successes combined, so from group 1 and group 2, over the total number of individuals combined, right? So sample size 1 plus sample size 2. So here, if you only have n and p hat, p hats for both of the groups, then you'd have to use this here, but it's easier to just think of the number of successes and the number of individuals, right? And so this is the p hat that we use for 2 sample proportions to check the normality condition for a hypothesis test. So this is the p hat, and q hat is, of course, where q hat is 1 minus p hat as always. Okay. For confidence intervals, right, we have to have at least 10 observed successes and failures in each group, which means we have to have, so for group 1, right, we have to check it. And again, right, q1 hat is 1 minus p1 hat, and q2 hat, oops, q2 hat is 1 minus, oh, p1 hat. Sorry, p2 hat. Oh, didn't make sense. There. Okay, so lots of conditions here. What's nice for you guys is, of course, that you are just working from home, right? And so when it comes time to the test, right, I expect to see all these conditions checked. And depending on if you're doing a hypothesis test or a confidence interval, right? Oh, I see my pointer is a little laggy here. Sorry about that, guys. Right, depending on if you're doing a hypothesis test or a confidence interval, still laggy, weird. That'll determine what conditions you need to check. So I will check for questions here. Let me go back there. Make sure we're all on top of things. Okay. Cool. Okay. So we'll start with the rundown for hypothesis testing, but notice that the actual steps that we do, right, nothing really changes at this point. So now that we've got, you know, a good handle on stating our hypothesis, doing the test, find the p-value, and stating the conclusion, right, we don't really have that much more to go through, right? We just need to know, okay, well, what's our new hypothesis? What's our new test? And then because I know I'm going to find a z-score here, right, then finding the p-value, I know how to do that already. And then our conclusion, I know how to do that too, because it's the same always. So here's our difference. So this, our hypothesis has to be about P1 and P2, right? The population proportion of group 1 versus the population proportion of group 2. And then by default, we'll have a not equal to in our alternative hypothesis. That depends on the question, right? We could have P1 is greater than P2, for example, P1 is less than P2. So the null hypothesis will always be P1 equals P2, right? And here I want to see use question specific subscripts, right? Especially, or at least in the null and alternative hypothesis, I want to see question specific subscripts, right? So the proportion of manatees, right, PM is equal to the proportion of platypuses, PP, right? And then how does PM compare to PP, right? And something like that, right? Doing the test, right, we said we're going to calculate a z-score, and so we're going to have P1 hat minus P2 hat. Again, it would be technically minus P1 minus P2, but we're assuming that they're the same, so it's always going to be 0, right? So not something to worry about. And then we've got the square root. This looks nasty, but it's not that bad, right? So the square root of P hat, right? P hat is not P1 hat, it's not P2 hat, it's its own thing, right? And so P hat, oops, is down here. And Q hat is, of course, 1 minus P hat. Okay. So P hat is the number of successes combined over the number of individuals combined, just like we talked about, right? And so you can calculate it like this, but if you know the number of successes in group 1 and group 2, you can just add them together and then take over the sample size of group 1 and group 2. We call this the pooled sample proportion, right? And so it's because we've kind of thrown them all into a pool, right? We've combined all the successes and then all the individuals. After we've got a z-score, right, we can use the z-table to find the p-value. If you have a two-sided test, right, then you're going to find your one-sided p-value and then multiply it by 2, right, because you've only got your z-table can only give you one of the tails, right? If you need a two-sided test, then you'd have to multiply that tail by 2. Once you have the p-value, right, you can draw your conclusion, and then just based off of how the p-value compares to the alpha level, right, if it's less than the alpha level, then you have enough evidence to reject H0 in favor of HA. And if it's not less than the alpha level, then you don't have enough evidence to reject H0. And then always state your conclusion in terms of the question, right? What does that mean in terms of the question? Okay. So let me see here. That's a question. So P1 hat and P2 hat are the proportion. That's right. Good. Good. So, like I said, I only have the one example, but it's going to be, so we're going to do everything with this example. We'll do a hypothesis test and a confidence interval. So I want to go through the confidence interval, but there's really not a whole lot going on, right? I show you how to build this confidence interval, and then the interpretation stays the same, right? We're some percentage confident that the interval from the lower bound to the upper bound captures the true difference in population proportions is what we're talking about here, right? And so that's what we're trying to capture. And so here, what's interesting is the confidence interval does not require the pooled proportion, right? And all we need is the sample proportions. So we've got P1 hat and P2 hat. So the proportions from each of the samples, plus minus Z star, we know how to find Z star from before, right? And then we've got P hat, Q, or P1 hat, Q1 hat. And this, you should know what Q1 hat is 1 minus P1 hat is at this point, and Q2 hat is 1 minus P2 hat. And then over, so P1 hat, Q1 hat over N1 plus P2 hat, Q2 hat over N2. So it's a lot of work, right? But it's not hard, right? You just need to plug in your numbers, be careful when you do your calculations, right? Simplify this number first, simplify this number separately, then add them together, then take the square root, right? So you want to start small and kind of balloon out big to get your margin of error. Okay, so I want to check for some questions before we go ahead and do the example. Okay. So here's our one mega example, I guess. So a surprising number of young adults, ages 19 to 25, is defined as a young adult, still live in their parents' home. A random sample by the National Institutes of Health included 2,253 men and 2,629 women in this age group. The survey found that 986 of the men and 923 of the women lived with their parents. Okay, so first things first, we are given a lot of information here, but if you kind of break it down, there isn't a whole lot, right? It's not like a two-sample means problem where you have to have the means of both groups, the standard deviations of both groups, the sample sizes of both groups, right? So there's a lot, I would say, less information that we have to deal with, which makes it an easier problem to do, in my opinion, but maybe you disagree. So here on this next page, I'll do example 7. First, I'm going to outline what we've been given. Oh, you know what? I'm just going to make sure I'm in the right. I'm not. That's okay. I'll deal with that later. I put it in the wrong file and I had a feeling. Okay, so we've been given first the sample sizes. So what I'm going to do is let group 1 be the males and group 2 be the females, right? It's men and women, but males and females. And so what we've got is we've got N1, I guess this is what's given there, move it down, easy peasy. Just so I'm not writing across a bunch of pages here. So N1 is going to be 2253, right? The sample size for group 1 is 2253. Sample size for group 2 is 2629. The survey found that 986 of these men and 923 of the women lived with their parents. So what we're talking about is a success in this case is considered living with your parents. And so P1 hat would be the 986 out of 2253. Right? And then 923 for the females. P2 hat is 923 over 2629. Okay. We could also let X be the number of successes. Oops. Number of successes, right? Depending on what's easier, because then we could say that X1 is 986 and X2 is 923. So then we could arrive at P1 hat is X1 over N1 and P2 hat is X2 over N2, right? These two proportions are the same, of course, right? This puts us up here. So what we're going to do is if you've got the patience, then you can use the exact numbers, 986 over 2253, 923 over 2629. It gets kind of annoying to deal with fractions all the time. And so, well, let's see what 986, let's see what's kind of reasonable. 986 over 2253. 0.437638704, right? So I've got P1 hat is approximately, right, because this is a decimal, 0.437638704, and P2 hat is approximately 923 divided by 2629. 0.351084064. To simplify things, how about we round this to 3 decimal places? Round the sample proportions to 3 decimal places to simplify our calculations. All right, otherwise we're dealing with these huge, and ideally if we were going to use exact numbers, right, we should use these fractions all the way through. And you can, if you just store them in your calculator, it's not that bad. And it is possible that when you do questions like this on My Open Math, I haven't run through the last assignment yet, but I think it potentially uses the exact values. So if you're finding the wrong answers, then maybe go back and try it with the exact numbers. I'll try to make it clear, but like I said, I haven't gone through it. In fact, I'll put it on my list right now. Go through assignment 10. My Open Math. Good. So what we'll use is, oops, P1 hat is approximately 0.438 and P2 hat is approximately 0.351. Okay. So we want to compare these two proportions, right? 0.351 is less than 0.438, right? These two are different, right? What we want to answer is maybe whether they're significantly different from each other, right? So that would mean that we want an alternative hypothesis with a not equal to sign in there if we're just looking, okay, are these two equal or no, right? If I want to know if P2 is less than P1, right, then I've got a one-sided alternative hypothesis, and that's going to dictate whether I need a one-sided or a two-sided p-value later. But for now, right, we haven't even started the question. We've just outlined everything that's given in the problem. Part A is a little bit of a starter, right? So how large is the difference between the proportions of young men and young women who live with their parents? And so part A, the difference in proportions, well, that's just going to be P1 hat minus P2 hat, which is 0.438 minus 0.351. So if we do 0.438 minus 0.351, I get a difference of 0.087. So this is the difference in the proportions of males and females who live at home. Okay. So that's part A. It's just kind of getting you started to find the estimate. And so here in part B, is there evidence? Whenever it asks, is there evidence, this tells me that I have to do a full-blown hypothesis test, right? So it looks like a small question here, but we know there's a lot of work involved. Is there evidence that there's a significant difference in the proportion of men who live in their parents' home compared to women? So we want to know if there's a significant difference, which means we just want to know, are they not equal to each other, right? And so that's going to determine our alternative hypothesis, right? So our alternative hypothesis must be that P1 is not equal to P2 then, if we want to know if there's a difference, right? Making this a two-sided test, right? So a lot of information is packed in there. And so what I'm going to do is I'm just going to copy this. Actually, I should keep the B in there too. Oopsies there. Copy. And part B, paste image, how about? I wonder if I can erase this. Cannot. Okay, well, whatever. So is there evidence that there's a significant difference in the proportion of men who live in their parents' home compared to women? I did not do a good job copying that, but whatever. Step 0, right? Remember, is that we have to check the assumptions. If we're doing a proportions question, right? And you'll know that you're doing a proportions question because usually the word proportion is in there, right? Which means we have to check the assumptions. One thing that I will say, right, and that I have been saying, is that if you're doing a hypothesis test here and then a confidence interval here, you're better off just checking all the assumptions at once. And then when you do the confidence interval, you can just say, oh, I checked the assumptions earlier, so I don't need to do that again, right? And so here, right, here we're doing a confidence interval. Check assumptions for both. Okay. So all those assumptions that we have to check. So we've got the first thing is independence, right? If we go back to our notes here, we have to check that we have independent observations. There's two things that we need to argue, right? But they apply to both of the samples. And then we have to check normality, depending on if we're doing a hypothesis test or a confidence interval, right? In this case, we're doing both, so we'll check all of these. So let's see here. The assumptions. First thing we have to do is check independence. In fact, maybe I'll scoot all this down. To the same page here. There. There. Now it's all on the same page at least. So independence. First thing we have to check is that we have a random sample, right? So here we just argue whether our sample was collected randomly or not. And so it says that a random sample, right, included this many of each. And so both samples were collected randomly, right? We just say it, or if it doesn't say, then we would just state it as an assumption, right? Here we're stating our assumptions / checking them. And so I'll say stated in the question. Okay. We have to have the 10% condition. Which says that N1, our sample size of group 1, is 2253. We just have to argue that that's less than 10% of the population of males, right? So the population that we're drawing from, males aged what, 19 to 25, right? And so that's the population that we're drawing from. Presumably the National Institute of Health is probably in the States. I haven't heard of the National Institute of Health. But is it reasonable to think that 2,253 is less than 10% of the population? Yeah, probably. And so here, of the population of males aged 19 to 25, right? You can say something like, so I'm adding this as an extra. If you just said this and the next part where we argue the same thing for N2, right, that's fine. Or if you want to get a little bit fancy, you could say something like, it is reasonable to assume that 2,253 is less than 10% of the population of males aged 19 to 25 in the States, presumably. I'll add that, but I don't know that for sure. So you could say something like that instead, right? But as long as you have this there, then I'm happy. And the next part, we do the same thing, right? N2, which was 2629, yeah. 2629, right, should also be less than 10% of the population of females. Population of females age 19 to 25. So again, a period there. We could write it out in words, right? But notice that the same information is here, right? So you have to have your sample size, you have to compare it. Is it less than 10%? And then of the population of males. So you can use this worded answer or this kind of shorthand answer. They'll be the same. You don't have to do both. But so you could say, if you prefer, it is reasonable to assume that 2,629 is less than 10% of the population of females aged 19 to 25. Right, so you could say that presumably in the States. So that's just checking our independence condition, right? Once you've seen a lot of these, then this will come very quickly, right? You have to make sure that it's random. Usually it's just stated in the question. So if it's not, you would say it's reasonable. So we use the same kind of, it's reasonable to assume that the samples were randomly selected, right? If it's not stated. Usually it'll be stated though. So then the normality condition, first let's do it for hypothesis testing, because this is the one that's different, right? Depending on if you're doing a hypothesis test or a confidence interval. So for hypothesis testing, we want, first we need to find p hat, the pooled proportion. So from your formula sheet here, let's have a look. From your formula sheet, it's on here, right? P hat is the pooled proportion, which is the combined number of successes. And if you need it, you can use the calculation. We don't actually need it because we can easily find the combined number of successes, right? And over the combined number of cases. So from your formula sheet here, copy and paste, put it there. So here, our p hat is the number of successes over the number of, or the total sample sizes. Total sample size. Here's where I find it's easier to just use, remember how we introduced, if you wanted to, you could call x1 the number of successes in group 1 and x2 the number of successes in group 2, right? And so if we need the total number of successes, right, we can rewrite that as x1 plus x2. So p hat becomes x1 plus x2 over n1 plus n2. P hat is, what was it? 986. Just gonna steal this information here. just so I don't have to keep scrolling around so much. I'll delete it in a little bit here. P1 or P hat is 986 plus 923, not 2. 923 over 2253 plus 2629. So my P hat is going to be what? 986 plus 923, 1909, over 2253 plus 2629 over 4882. So my P hat is roughly 1909 divided by 4882. Oops. Approximately 0.3910282671. Use P hat. Let's do 3 decimal places again. 0.391 to 3 decimal places. Because remember, for hypothesis test, right, we have to make sure that n times p hat is more than 10 and n times 1 minus p hat is more than 10, right? And so we need to check that np hat, which is, n1 p hat. Go back to our, because I seem to remember. Here's an error. I knew it. I remembered it just now. Should be, oops, should be n1 p hat has to be more than 10. n1 times 1 minus p hat has to be more than 10. And n2 times p hat has to be more than 10. And n2 times 1 minus p hat must be more than 10. That's a nasty hat, isn't it? Looks like a tilde. That's what we should be checking. I don't know where I got these from. Weird. Got them from somewhere. Because there's no total n, right? So that's what we're checking. I gotta fix that. N1 p hat, clean up this p hat. N1, we just said was 2253. 2253 times p hat, we said was 0.391. So if we multiply those 2253 times 0.391, I get 880.923. It's more than 10, which is good. N1 times 1 minus p hat is 2253 times 1 minus 0.391. 1 minus 0.391 times 2253 puts me at 1372.077, which is also more than 10. Like I said before, right, all these conditions that we're checking, they will check out, right? So it's not a matter of whether they check out or not. So if you try to tell me that no, it doesn't work, then you're wrong, right? So use that as a checkpoint for yourself. But it's just a matter of showing it and telling me that, okay, I know these are conditions that I have to check. And then we have to check that n2 times p hat, which is 2629 times 0.391. 2629 times 0.391 is 1027.939, which is of course also more than 10. Oops, more than 10. So that checks out. And then we've got the final n2 2 times 1 minus p hat, which is 2629 times 1 minus 0.391. 1 minus 0.391, 0.609 times 2629. Oops. I get 1601.061, which is more than 10, of course, so it all checks out. Yeah. This was for hypothesis testing, right? So if you were only asked to do a hypothesis test, then you would be done checking your assumptions, right? But now for the confidence interval, can you turn that off? Thanks. For the confidence interval, right, then my conditions that are on here are all good because they have a sample size for both. So then we have to have at least 10 observed successes and failures in each group. So what we'll do is you could use these calculations, right? But we know the successes and failures, right? Because if we use X as the number of successes, 986 and 923, out of the totals, right, we can figure out how many failures we had, right? So there's lots of ways that you could go about doing it. We need at least 10 successes and 10 failures in each group. Oops, that doesn't make sense. In each group there. So for the males, right, we had the number of successes, we called it X1 briefly, right, was 986, which is more than 10. The number of failures, well, if you're not a success, you must be a failure, so that must be N1 minus X1, which is 2253. 2253 minus 986. 2253 minus 986. 1,267 failures, which is also greater than 10. So both of these check out. So that's for group 1. Same idea for the females. The number of successes, X2, which was 923, which is definitely more than 10. I'll save my check mark for later. And the number of failures must be N2 minus X2, which is 2629. Yep. 2629 minus 923, which is 1706, which is more than 10. So both of these, of course, check out. And so therefore, assumptions for inference are satisfied. So it feels like a lot of work because we're going through it here together. And you know what, just to make it look a little bit better, oops, on the page here, scoot this up one, because this is on a new page. There. Okay, so you're working at home. There's no reason to not have some sort of outline for yourself of all the things that you have to check, right, to check these conditions. So I want to see it all done on the test. right? And so especially if it's a written test, but definitely it'll guide you through it if it's some sort of Moodle quiz. So these are all things that we have to check. Now that the assumptions have been checked and the assumptions for inference are satisfied, then we can go ahead and do our hypothesis test. So now we can move on to step 1, which is to state the hypotheses. So again, recall that group 1 is the males and group 2 is the females. So then my null hypothesis is going to be how P males, compares to the proportion of females, PF. My alternative hypothesis, remember, we just wanted to know if there was a difference. So we want to know, is PM not equal to PF, right? Because here we wanted to know, is there a difference? And so this here, this not equal to, makes it a two-sided test, right? So the sign comes from the question, and then the sign determines if you have a two-sided or a one-sided test. Okay. So step 2, do the test. Right. Z is, and I'll just go to your formula sheet so you see where it is here. Copy. Z is P1 hat minus P2 hat over the square root of P hat times 1 minus P hat, times 1 over N1 plus 1 over N2. Okay. Notice that this here is the pooled proportion found earlier. And we said P hat, the pooled proportion, is 0.391. Whereas P1 hat and P2 hat we also found earlier, just using the information that we were given. Let's see here. Oops, let me copy this here. Copy. Maybe I'll put this, I'll just stack them on top of each, stack them on top of each other here. Move them over here. So P1 hat, we decided to 3 decimal places was 0.438, and P2 hat was 0.351. Notice that these are all different, right? And so you want to make sure that you use them in the right spots. So here, I'm not going to go ahead and use PF or P hat M and P hat F because it gets confusing, as you saw, right? And so I'm going to use P1 and P2 because I've already defined the groups, right? It's only in the null and alternative hypothesis that I really, really want to see these subscripts or question-specific subscripts. So here, I've got Z is P1 hat, which is 0.438 minus 0.351 over the square root of 0.391 times 1 minus 0.391 times 1 over n1, which was 2253, I want to say. Yep. 2253 plus 1 over n2, which was 2629, but let me just confirm that. Okay. So I'm slowly going to work my way through here. I can simplify the numerator separately from the denominator, right? And so I can simplify the top and bottom separately. So z is 0.438 minus 0.351. That's that difference that we found in part A, right? And so that's the difference that we're talking. This is the sample difference in proportion. We want to use this to talk about the population difference in proportions, right? 1 minus 0.391. I get 0.391 times 0.609 times 1 over 2253 plus 1 over 2629. I'm not going to worry about writing out all the steps here because it's going to be easier if you just do these in your calculator. But the important thing is if you find this separately, then add them together, right? So using a store function in your calculator is going to be a good idea. Then multiply it by 0.609, then multiply it by 0.391, and then take the square root. So I've got 1 over 2253, oops, did the wrong one. 1 over 2253 is really small. I'm going to store in A, okay. And then 1 over 2629 plus recall A equals, okay. And then I'm going to do times 0.609 times 0.391. So what I get is I get 0.087 over the square root of 0.0012, and it's giving me in scientific notation, but that's okay. 3019534765. Let me just make sure here. 1, 2, 3, 4. Good. Making sure that I did it right. Taking the square root of that, I get 0.087 divided by 0.01737680858. 0.087 divided by that, I get a z of fairly large z, 5.006673095. Z, we have to round to 2 decimal places, right? Here, this is going to be off the table, but that's okay, right? So Z is approximately 5.01 to 2 decimal places to match the Z table. So what I'm going to find here, right, in my step 3, so now I'm done with step 2, I'm moving on to step 3. Step 3, find the p-value. If I imagine here is my Z, Z is centered on 0. I'm finding a Z equal to 5 here, 5.01, let's say. Right? It's way out in the tails. I know just from what we've been doing before when we're out in the tails like this, the table stops at 3.49. So what we do at this point is that we can say, okay, well, this area is the one-sided p-value is approximately 0. Right? Even if we double that on this side, because we need the two-sided p-value, it's going to be approximately 0 times 2. it's still going to be really small. And so what we have is the two-sided p-value is the one-sided p-value times 2. So that's going to be close to 0 times 2, which is still going to be close to 0 or approximately 0. I know that probably feels a little bit like witchcraft here, but that's just how we do it, right? So we say, okay, well, this area is super, super small. Even if I have 2 of them, it's not going to get me close to not rejecting the null hypothesis, right? So when I'm far out in the tail like this, it just tells me that I'm definitely going to reject the null hypothesis, right? So my two-sided p-value is approximately 0. It's so important that you say approximately 0 because it can't be 0. So now we've got our p-value. So now in step 4 is our conclusion. Remember, we have 3 parts. So since our two-sided p-value, so first part, we have to compare our p-value to the alpha level. Since our two-sided p-value of approximately 0 is less than the alpha level, less than the alpha level of 0.05, right? You can say assumed alpha level, I forgot. We have enough evidence to reject H0 in favor of HA. I'll add that. Don't have to, but in favor of HA. So what does that mean in terms of the question? It's been so long. Do we even remember the question? Or let's see here. I'll go back to the original. Copy. Oh. Right, so here's the question. We're going to reword the question as an answer. Is there evidence that there is a significant difference in the proportion of men who live in their parents' home compared to women? Yes, there is evidence. Therefore, there is evidence. Right, just reword the question as an answer that there is a significant difference in the proportion of men, who live in their parents' homes compared to women. Right, so just to reword the question as an answer. Nice. Okay, so I know I think I'm cutting it close here on time, but I think we have time to do the confidence interval, which is the last part. And let's see here. Where was it? So I want to construct a 90% confidence interval for the difference in proportion of men and women who live in their parents' homes. Because I've checked all the conditions already, or I've checked all the assumptions, I can just go ahead and do the confidence interval. And so here, picks the image, learn from my lessons here, learn from my mistakes, I should say. So here, since we have since we have already checked the conditions, oops, we do not need to check them again. You probably noticed it took a long time, right? So you don't want to be doing that twice if you don't have to, right? So that's why we just do it once, check them all, and then we can just kind of answer all the problems. So from our formula sheet, right, the confidence interval for two sample proportions is this one here. Notice that there's no mention of a p hat, right? We've just got our p1 hat, oops, sorry, p1 hat, p2 hat, z star, we know how to find that, p1 hat, p1 hat, p2 hat, p2 hat, n1, n2. We have all that information in the question, right? So we know, I'll just steal our p1 hat, p2 hat from earlier here. Where did I put them? Oh yeah, here. P1 hat, copy. P2 hat, paste. Okay, so P1 hat, P2 hat, N1 is, keep forgetting what it is, 2253, I want to say. 2253 and 2629. 2253 and N2 is 2629. And so we've got P1 hat, P2 hat, we've got P1 hat, P1 hat, N1, P2 hat, P2 hat, N2. All that information is just here, right? And so Z star for a 90% confidence interval, right, is going to be in our table. So we go to our Z table and we find that a 90% confidence interval gets us a Z star of 1.645. So we use that here. Z star is 1.645. Now we can just construct our interval. And so we have P1 hat, which is 0.438, minus P2 hat, which is 0.351. Notice that this here, this is the difference that we found in part A. So again, we're building a confidence interval around the difference in the population proportions, plus minus 1.645 times the square root of 0.438 times 1 minus 0.438 over 2253 plus 0.351 times 1 minus 0.351 over 2629. Right? Lots of work here, but once you plug in all the numbers, right, you just need to remember to go slow. Don't do any illegal math here. And we can simplify. So 0.438 minus 0.351 is still 0.087 plus minus 1.645. I'm going to leave that while I simplify this square root here. Notice that this square root is not the same as we did in the Z test, right? So we can't reuse it. We have to use this new one. I think. Oh yeah, it is, because it uses p hat. So we've got 0.438 times 1 minus 0.438 divided by 2253. And I'm going to store that. So notice that I'm just using the store function just on the side here. So I'm actually not going to do, I'm just going to do a square root of one number. And then I'm going to deal with this portion, so I'm going to do 0.351 times 1 minus 0.351 and use brackets. Make sure that you get to the same number that I do in the end here, divided by 2629 plus, okay. Uh-oh, I did it wrong. 0.351 times, because my calculator, every time I hit enter, it does whatever I told it to do again, and I think I hit it twice. Plus, recall. I am getting the square root of 0.0001959055262. There is a huge chance that that's wrong, but just check it and make sure that you get the same thing. 1, 2, 3, 4. Okay. I'm going to go ahead and use that though. The square root of that is 0.01399, so times 1.645. I get a margin of error of 0.023024449, right? 0.087. Notice that this is your margin of error. So now for our confidence interval, right? And I was getting a lot of questions about this on the first proportion or confidence interval assignment, right? Your confidence intervals have to be in round brackets, lower bound separated by a comma, then upper bound inside there. So we get, I'm going to store this, see, 0.087 minus that, I get 0.063975551 up to 0.087 plus, recall C, 0.1100244449, or if we want to go to 3 decimal places, 0.064 up to 0.110. We're so close. We just have to interpret this thing, remembering that we're talking about the difference in proportions, but also using the question, right? So construct a 90% confidence interval for the difference in proportion of men and women who live in their parents' homes, right? So our interpretation always starts the same. So we are 90% confident that the interval from 0.064 to 0.110, right? Notice that these are proportions, so that's 6.4% to 11% if you want to convert them to percentages, but we won't because we want to talk about the proportion. Captures the true proportion, and then here's where we just use whatever the question, sorry, the true difference in proportion. That's what I should have said. The true difference in proportion of men and women who live in their parents' homes. Of men and women, oops, who live in their parents' homes. Ta-da! Hey, right on the money. But here we are. The end. I'm sad, but also I'd be way more sad if we were meeting in person, because but now we've kind of had this weird term anyway. So that is the end of the material for this course for you guys. So pretty exciting. All right. So Oh yeah, we do have a class. Oh, sorry, Sky. So you were getting a different answer for the square root portion. I might have done something wrong. I'll double check it. And yes, we do have a review class on Wednesday. Yes, review, whoops, on Wednesday. Woohoo. But that's the end of the material. Laura says, sorry, so for the midterms, if the mean was better on the second, the midterm would be weighted, and how much more? Well, so that depends. So I haven't looked at those numbers because there's been a lot of other stuff going on. So how about I'll give you those weightings and I'll adjust those weightings on Moodle too. So I'll give you those on Wednesdays or on Wednesday. Awesome. So I'll just add it to my list here. Test weights for Wednesday. Good. Awesome. Any other questions? So like I said, Sky, I'll check my math. Very possible that I did something wrong because like I said, my calculator was being a little fidgety. All right. Thanks, guys. Quote unquote, see you on Wednesday. See ya. Class down.